Good morning. My name is Sliman Metir. I will do the presentation on behalf of Mr. Ahmed Kallel, the first one on the list. I am a research assistant at the University of Sherbrooke in the same group of Mr. Radwan Masmoudi. The authors of this publication are Ahmed Kallel, which is a PhD candidate at the University of Sherbrooke, Mr. Radwan Masmoudi, professor at the University of Sherbrooke, which is here with us, Benoit Bissonnette, professor at the University of Laval, and Marcelin Joannis, professor at the École Polytechnique de Montréal. So my presentation will contain an introduction and objectives, experimental program, test results, discussions, and conclusions. The use of carbon fiber reinforced polymer CFRP is being increasingly recognized for rehabilitation and strengthening of concrete structures. This technique comes to solve various problems and increase the lifespan of concrete structures. The technique of externally bonded CFRP composites have been used to increase both flexural and shear capacity of concrete elements, including girders and slabs. In addition, axial capacity of columns can be increased with CFRP wrapping. So, for shear strengthening, CFRPs are bonded to the lateral face of concrete beams. For flexural strengthening, CFRP are bonded in the tension side. The fibers are oriented in the longitudinal direction to increase flexural properties. And for axial strengthening, CFRP encircle the structure and prevent concrete expansion under compressive load. The choice of CFRP is based on several advantages. They are lightweight materials with a low density compared to steel. They have high modulus and tensile strength. CFRP have an excellent fatigue resistance compared to steel and aluminum. And the ease of installation as well as their adaptation with complex shapes. However, this technique still has limitations, such as the durability of the bond between CFRP and concrete, which is caused by environmental exposure, existing structural conditions, and fatigue loads. According to the literature review, the effect of freeze-thaw cycles on the bond of CFRP concrete joints is a very critical factor to consider, especially for structures exposed to northern weather. The findings, or some findings of previous research in this field, are presented in this table. We can say that some studies have shown an improvement of bond properties after freeze-thaw cycles. In the other hand, other studies have shown opposite results, with a negative effect of freeze-thaw cycles on the bond between CFRP and concrete. So, given the contradictory results found in the literature review on the effects of freeze-thaw cycles on the bond between CFRP and concrete, this paper aims to confirm one of the two existing results by investigating the bond behavior of CFRP sheet concrete joints under static loading after 100, 200, and 300 cycles of freeze-thaw in humid conditions. The aim of this research is to simulate the service life conditions of bridge structural elements, strengthened with CFRP fabrics by exposing them to freeze-thaw cycles in the presence of moisture on the surface. The single lab shear test was used in this experimental program to evaluate the bond performance between CFRP and concrete. The details of the specimen are obtained from ASTM standard. As shown in the left figure, the concrete blocks dimensions are 150 by 150 by 400 millimeters. The width of the CFRP strip is 50 millimeters. The bond length equal to 300 millimeters, where the effective bond length is obtained by the equation on the left, by ECI 440. For this experimental program, 4 control specimens were tested under static loading until failure without conditioning to be considered as reference results. 3 series with 4 samples each were tested after 100, 200, 300 freeze-thaw cycles. In addition, 3 cylinders were tested for each freeze-thaw cycles. For the application of the CFRP on the concrete, the wet layup procedure was used. The first step is the preparation of the concrete surface. Very important step. According to the CFRP suppliers' recommendations, CSP3 to CSP5 surface profiles should be obtained prior to apply the CFRP. The International Concrete Repair Institute indicates that the sandblasting method is one of the most effective methods to achieve CSP3 to CSP5 surface profile. So the second step is applying the primer epoxy resin. After that, applying the adhesive layer, which is epoxy paste. Fourth step, the impregnation of the carbon fiber fabric strip with epoxy resin. Fifth step, the installation of the CFRP strip. And finally, applying a pressure with a roller in order to eliminate any voids. Going to present the freeze-thaw exposure, the environmental room temperature was set between minus 25 degrees Celsius and plus 10 degrees Celsius to obtain a temperature range of minus 18 to plus 4 degrees inside the concrete, as recommended by ASTM standard. To maintain the moisture of the CFRP concrete joints during the freeze-thaw cycles, the samples were covered with water-saturated fabrics. So 2 freeze-thaw cycles per day were performed. After freeze-thaw cycling, each sample was instrumented with 4 string gauges placed on the CFRP strip along the bond length. In addition, an LVDT was installed at the beginning of the bond length to record the slip of the joint during testing. The specimen was inserted into a conventional tensile load frame so that direct shear can be applied on the CFRP concrete interface. Then each specimen was tested in tension to failure at a load rate of 0.3 millimeters by minute. Going now to present the experimental results. The mode of failure of the control samples, the CD1, was a cohesive failure in concrete substrate with approximately 2 millimeters of concrete remaining attached to the CFRP sheet. After 100 freeze-thaw cycles to series 2, cohesive failure in the concrete substrate was also observed, where a thin layer of 1 millimeter of concrete remained attached to the adhesive layer. The failure mode of the specimen tested after 200 freeze-thaw cycles, also series 3, was a mix between partial cohesive failure in the concrete plus a partial adhesive failure in the interface. Finally, the failure mode of the specimen tested after 300 cycles, freeze-thaw, so it's series 4, was a total adhesive failure at the CFRP concrete interface. The strain profiles of CFRP concrete joints were plotted at 5 kilonewton, 10 kilonewton, 15, 20, 25 kilonewtons, and at the maximum load. It was observed that up to 25 kilonewton loading, the damaged bond length was 75 millimeters of the total interface length for the control samples, 150 millimeters after 100 freeze-thaw cycles, 225 millimeters after 200 freeze-thaw cycles, and finally 75 millimeters after 200 freeze-thaw cycles. The left figure presents the load versus global slip curves, which were obtained from the LVDT recording data. And the right figure shows that bond capacity of CFRP concrete joints was increased by 3%, 13%, and 21% after 100, 200, 300 freeze-thaw cycles respectively. This graph on the left shows that freeze-thaw cycles led to a slight increasing in concrete compressive strength of about 2 to 4%. And considering what we saw about the failure modes of each test series, it can be stated that the increase in bond capacity of samples tested after 100 cycles can be explained by the increase in concrete compressive strength, and the increase in bond capacity of the samples tested after 200 and 300 freeze-thaw cycles can be related to the change in the mechanical properties of the adhesive layer due to freeze-thaw cycles. The bond stress versus slip curves were developed to provide a good evaluation of the effect of freeze-thaw cycles on the bond behavior of CFRP concrete joints. The fitting parameters of the experimental curves of the applied load versus slip were introduced in DIE model to construct the exponential form of the bond stress versus slip. It was also found that the bond strength increased by 13%, 35%, and 46% after exposing the CFRP concrete joints to 100, 200, 300 freeze-thaw cycles respectively. In conclusion, the purpose of this study is to investigate the bond behavior between CFRP sheets and concrete after freeze-thaw cycles in wet conditions. The following conclusions can be drawn. Cohesive failure in the concrete substrate was observed for control samples as well as after 100 freeze-thaw cycles. From 200 freeze-thaw cycles, the failure mode of the CFRP concrete joints changed to adhesive failure at the CFRP concrete interface. This change in failure mode allowed stating that the CFRP concrete interface was affected by the increase of freeze-thaw cycles by presence of moisture during the freeze-thaw exposure. The maximum bond stress increased by 13, 35 and 46% compared with the reference results after exposing the CFRP concrete joints to 100, 200, 300 freeze-thaw cycles respectively. The improvement of the bond stress was related to the change in the mechanical properties of the adhesive layer. And we recommend that to study the effect of freeze-thaw cycles on the adhesive properties in further researches. The authors would like to acknowledge the Natural Sciences and Engineering Research Council of Canada for its financial support, the technical staff of MAPI for the CFRP materials provided for this research, the Composite Structures and Materials Research Group headed by the Professor Radwan Masmoudi, and the technical staff of the Department of Civil Engineering and Construction of the University of Sherbrooke. Thank you.